Hello my friends, and welcome back to the You Can Do TV channel. At Antamina, open-pit mining begins high in the Andes at over 4,500 meters above sea level. The extraction process involves drilling, blasting, and loading rock into large haul trucks. The ore is then crushed and transported through a long mineratic to the coast. With advanced technology and strict safety and environmental standards, high-grade copper concentrate is produced. This transformation of an ancient deposit into a world-class operation reflects both the engineering achievements and the dedication of thousands of workers. Every step in this process contributes to Peru's growth and showcases responsible mining at a global standard. Raw materials including limestone, shale, and sandstone are quarried and crushed into fine powder. This mixture, called raw feed, is blended in the correct proportions and ground in a vertical roller mill. It is then preheated to about 900 degrees Celsius before entering a rotary kiln, where it is heated to 1,450 degrees Celsius to form clinker. The clinker is cooled using air, then ground with gypsum in the cement mill to control setting time. The resulting fine powder is cement, which is stored in silos before being transported to customers. Waste materials like glass and iron waste are also used in the process. The construction of the Rusky Island Bridge, a cable-stayed marvel with a 1,104-meter main span. This ambitious project required installing 2,860 kilometers of cable strands, including record-breaking 582-meter cables, the longest ever manufactured for a cable-stayed bridge at the time. These cables supported a bridge deck elevated 70 meters above the eastern Bosphorus Strait to ensure navigation clearance, connecting Vladivostok's mainland to Rusky Island. The installation process faced significant challenges due to the harsh environmental conditions of Vladivostok, with temperatures frequently dropping below freezing, sometimes as low as -30 degrees Celsius on the exposed deck. A critical task was assembling and installing high-density polyethylene ducts, some exceeding half a kilometer in length. These ducts were hauled over 300 meters vertically to the bridge's 320-meter high towers. The extreme length of the ducts rendered standard installation methods ineffective, which typically used a single strand for alignment. Instead, Freycinet, responsible for cable installation, employed 2 strands to hoist and secure the ducts in position before threading the remaining strands. Welding these ducts on the deck was particularly challenging due to the frigid conditions. To mitigate this, a heated and insulated shipping container was set up on site, creating a controlled environment to ensure weld quality. To reduce wind forces on the towers, Freycinet designed a compact cable-stayed system using optimized diameter HDPE ducts encasing compact strands. This required developing new threading tools to fit the limited space within the ducts. The iso-tensioning equipment was upgraded with a 300mm stroke, a 50% increase, to accommodate the cable's significant length and sag. Internal and external dampers were installed at the base of shorter and longer cables, respectively, with external dampers providing up to a 6% in-plane logarithmic decrement for the longest cables, effective from -40 degrees Celsius to +65 degrees Celsius, even at low vibration amplitudes. Safety was paramount at the tower tops, where workers were exposed to extreme conditions. Solo working was banned, and staff were trained to detect frostbite and hypothermia. Low temperatures risked equipment failure by affecting hydraulic fluids, so insulation and oil heating were applied to maintain reliability. The project was completed in July. The chip seal process begins by spraying a layer of RS2 asphalt emulsion onto the road surface. A spreader then distributes crushed stone, usually size 8, over the asphalt. The spreader hooks onto a truck and makes several passes. Typically, 2 to 3 coats are applied to enhance durability and create a cost-effective, lasting road surface. The H-Series hydraulic multi-cylinder cone crusher crushes materials through high-speed rotation and layered pressure. Raw stones or ores enter the crushing chamber, where the mantle moves eccentrically against a concave surface. This compresses and breaks the material repeatedly. Multiple crushing cavities, medium, fine, and superfine, allow control over output size. Hydraulic adjustment systems enable rapid setting changes, optimizing the crushing circuit for maximum efficiency. The hydraulic system also facilitates cavity cleaning and overload protection, minimizing downtime and ensuring continuous, automated material crushing with consistent output quality. The chipping and sealing process begins with a uniform layer of hot liquid asphalt binder sprayed onto the prepared road surface using a spreader truck. Immediately after, a dump truck equipped with a chipping spreader carefully spreads a layer of clean aggregate, typically crushed stone, onto the hot asphalt. The stones are evenly distributed and embedded in the binder. Workers use brooms to spread the aggregate-covered asphalt evenly over the entire road surface. Next, heavy rubber-tired rollers make multiple passes over the surface to press the aggregate into the asphalt, ensuring proper bonding and creating a tight, compact layer. This step is critical to minimizing stone loss and ensuring surface durability. After rolling, any excess loose stones are mechanically removed with brooms for added safety and finish quality. The chip and seal solution demonstrates the importance of timing and coordination, as delays can result in poor bonding or uneven coverage. Overall, the process presented is efficient, with traffic resuming immediately upon completion. This crumb coating method provides a cost-effective, quick-to-install, and weather-resistant road surface, ideal for rural and low-traffic areas. The chip fabric overlay process begins with the road surface being cleaned to remove debris. A uniform layer of asphalt emulsion is sprayed onto the road surface. A geotextile is then carefully laid over the emulsion, ensuring full coverage and adhesion. A second layer of asphalt emulsion is applied over the fabric. Next, a uniform layer of chips and aggregates is laid over the surface. The chips are rolled and compacted to embed them in the emulsion, creating a durable overlay. Finally, the loose chips are swept away, leaving a smooth, protected road surface. To repair a damaged pavement with Fast Patch DPR, first clean the area to be repaired. Open part A of the polymer and pour it into the mixing bucket with the aggregate. mixing well while scraping the sides and bottom. For asphalt, add the black bag. Then, open part B of the polymer, pour it into the center and mix for another minute. Immediately pour and spread the mixture over the damaged area, using a trowel or grater to level it with the surrounding surface. Sprinkle sand evenly over the mixture until it is completely covered. Clean tools immediately after application. The repair will cure in less than 45 minutes. The CMPRO 1600 begins the cage making process by feeding longitudinal bars into the rotating cage support system. A steel wire spiral is then continuously wrapped around the bars with a variable pitch. The zero pitch function allows the spiral to begin with no spacing, ensuring strong joints at the start. As the spiral wraps, the SAF 3000 fully automatic welding unit welds the intersections, securing each contact point. The pitch can be adjusted on the fly using the machine's 8-inch color display. The hydraulic cage maintains alignment throughout the process. Once the cylindrical cage reaches the desired length, it is unloaded, completing a highly efficient and automated manufacturing cycle suitable for cage diameters up to 1,600 millimeters. Track and sleepers were first removed, followed by Phase 1 excavation of the embankment. The king post wall was dismantled, and bentonite was applied as the sliding medium. After hydraulic jacks and the control system were installed and tested, the bridge slide began at 9 p.m. on Christmas Day. The concrete structure, weighing 3,750 tons, moved at an average speed of 3 meters per hour. Phase 2 excavation occurred near the structure during the slide. The operation was completed at 8:15 a.m. on Boxing Day. Earthworks were reinstated and the track was restored, completing the project efficiently and on schedule. In December, a 12,600-ton precast concrete box bridge was slid 165 meters across the M42 motorway near Marston using Freycinet's auto-repage technique. Constructed 80 meters away from the motorway, the box sat atop a specially designed guide raft. The raft was cast in 2 phases due to site constraints, with embedded concrete upstands for lateral guidance. Nine 52-strand cables anchored at the raft's far end, passed beneath the box, and connected to active deviators within the box's base slab. 9 1,000-ton jacks pulled these cables, progressively advancing the box at a steady pace of 4 meters per hour. Innovative winching methods and cast-in troughs allowed post-construction cable installation. As excavation works proceeded in phases, the box crossed first the southbound carriageway, then the central reservation, and finally the northbound lanes. The entire operation, completed in under 36 hours and ahead of schedule, was the world's longest box slide. It minimized traffic disruption, enhanced worker safety, and exemplified the benefits of a well-integrated engineering and construction team. The I-90 Snoqualmie Pass East project involved upgrading a 15-mile stretch of highway to improve safety, expand from 4 to 6 lanes, and enhance ecological connectivity. Key improvements included constructing multiple undercrossings and the first wildlife overcrossing on a Washington interstate, allowing animals like deer, elk, and mountain lions to safely cross. Avalanche bridges and wider structures at Gull Creek improved hydrology and connectivity with wetlands. Box culverts were replaced with bridges and natural stream beds, aiding species such as the coastal giant salamander. Native vegetation was planted to restore habitats, and wildlife fencing was added to guide animals towards safe crossings and reduce road mortality. Crews used the massive tunneling machine Bertha to excavate the State Route 99 tunnel beneath Seattle. After completing the 9,270-foot route in April, Bertha broke through into a specially built disassembly vault. Over the next 4 months, workers cut apart and hoisted roughly 8,000 tons of steel and machinery from within the tunnel. The components were loaded onto trucks and removed piece by piece. This complex disassembly process was necessary because the machine's parts were too large to extract whole. Once the tunnel was cleared of Bertha's remains, crews proceeded with constructing the interior double-deck highway and installing operating systems. This marked the final phase before opening the tunnel to traffic, completing one of the most challenging infrastructure projects in Seattle's history. On April 4th, Bertha, one of the world's largest tunnel boring machines, completed its 1.7-mile underground journey beneath downtown Seattle. In its final foray, Bertha chewed through more than 1,000 tons of reinforced concrete and fiberglass that had sealed the tunnel's exit. The process began with the cutter head slowly grinding into the thick wall, creating a rumbling and cracking sound as debris fell away. Hydraulic arms inside the machine continued to press forward, crushing and transporting the material through a massive conveyor system. As Bertha advanced inch by inch, the powerful rotation of the cutter head made steady progress past the final hurdle. After several tense minutes, the cutter head emerged completely, marking the successful end of the tunneling operation and demonstrating the scale and power of the massive machine. The ring building process begins as the erector rotates to pick up the next tunnel segment. The segment is lifted and carefully positioned into place. Hydraulic jacks retract to make room for the new segment. Bertha then installs the segment, securing it to form part of the tunnel ring. This sequence repeats until 10 segments form a complete ring. Each ring contributes to the outer wall of the State Route 99 tunnel, with a total of 1,450 rings required for completion. Workers begin by installing 2-foot thick concrete segments to form the tunnel's circular wall. Once enough tunnel is completed, crews construct corbels foundation ledges for building walls and decks. Reinforcing steel is placed, formwork is installed, and concrete is poured, cured, and covered for 28 days. Walls are then built upright on the corbels with steel reinforcement and concrete, each panel containing 13 tons of steel. After curing, an upper roadway deck is constructed between the walls, using epoxy-coated steel and oil-treated formwork. Finally, a precast lower roadway is set onto the corbels, completing the double-deck highway inside the tunnel. The construction of the Linth-Limern Dam took place over 3 summer seasons on Europe's highest large-scale construction site. The dam, more than 1 kilometer long, is a massive gravity dam with a triangular cross-section designed to withstand the enormous pressure of the reservoir water. Unlike an arch dam, it cannot rely on steep mountain flanks for support, so its base is very wide and heavy to ensure stability. Building the dam at 2,500 meters altitude posed significant logistical challenges. The main building material was excavated rock from nearby caverns, transported uphill by a construction cableway requiring over 20,000 trips. From an intermediate storage area, the material was processed, crushed, SRTED, and stored in silos. This gravel then supplied the on-site concrete plant. The dam consists of 68 individual blocks, each 15 meters wide. Construction began with every second block to serve as formwork for the others. Blocks are built in 3-meter-high stages, with careful alignment of formwork and interlocking features between blocks. To prevent cracking, cooling pipes were installed in the large base stages to control the heat generated during concrete curing. Concrete was poured in layers of 50 centimeters, which had to be vibrated and compacted quickly before the next layer was applied, typically within 2 hours. The pouring of one block stage could last up to 12 hours. Surfaces were roughened with high-pressure water jets to ensure proper bonding with subsequent stages. Work continued 24/7 during the short construction seasons, adapting to unpredictable mountain weather. By November, the dam section was completed, with final parts and the dam crest finished. On April 5th, a convoy of over 20 low loaders departed from Vigotel Motorway Junction, heading to the A1 motorway near Reesville, with traffic rerouted to the hard shoulder to maintain continuous flow. The construction of the Astra Bridge, a 250-meter-long, 1,250-ton mobile bridge, 7.3 meters wide, commences. This modular structure enables road restoration beneath, while ensuring uninterrupted traffic overhead, eliminating lane closures and minimizing congestion. The assembly process utilizes heavy goods vehicles and cranes, supplemented by self-unloading components to optimize efficiency. Upper ramp elements, each weighing 57 tons, are transported on 6 heavy-duty bogies. These elements are precisely aligned using hydraulic systems and bolted together, forming a personal unit. Concurrently, lower ramp halves are unloaded and assembled with high-precision coordination. A specialized rounding element is installed to ensure a smooth transition onto the bridge, securely connected to the lower ramp's base. Hydraulic lines and data cables are meticulously integrated to support structural and operational functionality, and the upper ramp is docked, creating a 16-bogie assembly. This process is replicated for the opposite ramp, ensuring structural symmetry and operational stability. On the second night, the central bridge section is constructed over 8 hours, with simultaneous assembly from both ends to maximize efficiency. The bridge employs 3-part intermediate segments within mobile gantries. The central segment interlocks with counterparts using pivot-mounted pins, secured by wedges to prevent lateral displacement. Edge segments are then installed, with 18 bridge portals and 57 intermediate segments incorporated. Each gantry unit, assembled in 30 minutes, extends the bridge by approximately 20 meters and 8 bogies per hour per side. The gantries, the bridge's structural core, rest on robust base plates during operation, but are designed to reduce to a 3.5-meter width for transport. Lifting cylinders elevate them for bogie mounting, with base plates swiveled into position, impact guards secured, and wheels adjusted for mobility. Hydraulic controls enable precise maneuvering, with a 2-kilometer turning radius. Wedges are slightly loosened post-assembly to accommodate thermal expansion and contraction, ensuring long-term structural integrity. The bridge's development involved 15 years of steel fabrication, 8 years of design, and 12 years of technical installation. Extensive training ensures assembly precision matches digital simulations. After 2 night shifts, the bridge nears completion, with 50 bogies per side and the final edge element installed. Road restoration begins beneath, milling 4.5 centimeters of worn surface. Dumpers facilitate material transport, and standard machinery operates unimpeded under the bridge. A chipping layer is applied to enhance surface bonding, followed by the application of new pavement. The bridge's design enhances safety, shielding workers from overhead traffic and weather, enabling daytime operations and reducing night shifts. The following night, under low traffic conditions, the bridge is relocated to the next construction segment using 100 bogies, guided by GPS for centimeter-accurate positioning. It is then reopened for traffic, ensuring project continuity and operational efficiency. Begin the asphalt repair process by applying a coat of liquid asphalt to the cleaned and prepared damaged area. Use a high-quality asphalt emulsion, ensuring it is appropriate for the ambient temperature and pavement conditions. Apply the asphalt using a spray system, maintaining a consistent application rate of approximately 0.05 to 0.15 gallons per square yard, depending on the porosity of the surface and the size of the repair. Ensure the liquid asphalt forms a thin, uniform layer to increase adhesion between the existing pavement and the new asphalt mix. Allow the asphalt to cure until it becomes tacky, typically 15 to 30 minutes, depending on weather conditions and product specifications. Workers fill potholes or cracks with asphalt repair material. Choose a high-performance cold patch mix, polymer modified for optimal durability. Pour the mix into the prepared area, filling approximately 1 inch deep to account for compaction. Use a rake to spread the material evenly, making sure it fills all voids and extends slightly beyond the repair boundary for a seamless transition. For deep potholes over 2 inches, spread the mixture in layers 1 to 2 inches thick, compacting each layer before adding the next to avoid settling. Compact the asphalt mixture with a roller for repairs to large areas. Apply firm, even pressure to secure the material, eliminate air pockets, and form a dense, stable patch. Work from the edges inward to ensure even compaction. checking for a slight bump on the surface to promote runoff. Continue compacting until the patch is flush with the surrounding pavement, typically achieving 95% of the maximum theoretical density. Smooth the surface with a lute to a glossy finish, ensuring no loose aggregate remains. For major repairs, use a small asphalt roller to increase compaction and evenness of the surface. Allow the patch to cure for 2 to 4 hours, or as directed before resuming traffic. Monitor the repair for signs of settling or cracking, addressing issues promptly to ensure long-term performance. This creates a durable, level surface. Hot pour asphalt crack repair begins by heating the solid sealant in a melting furnace until it becomes liquid. The hot material is then poured directly into the prepared crack using both the cup and trowel methods. It is applied flush with the surface or with a thin strip to ensure a tight seal. This method allows the sealant to bond effectively to the crack walls. After application, the sealant is allowed to cool until it is no longer hot or tacky. The thermoplastic material is first heated in a specialized melting furnace until it reaches a molten state suitable for application. Once fully melted, the material is transferred into the heated hopper of the striping machine. The machine then sprays the molten thermoplastic onto the cleaned road surface via a spray bar, with operators moving the machine to create thick, precise lines in the desired pattern. Once the thermoplastic is applied, it is spread and shaped by the machine to ensure uniform thickness and coverage. Once applied, the material cools rapidly, hardening into durable anti-slip markings. Throughout the process, the operator carefully monitors the temperature and flow of the thermoplastic to maintain consistency and quality. This method produces highly visible, long-lasting road markings that enhance pedestrian safety. At Kanban, iron ore is extracted through open-pit mining. The mined ore, which has a high crushability index, is transported to a dedicated crushing and screening unit supplied by Metso. Here, large lumps of ore are first fed into a primary crusher for size reduction, with workers using dump trucks to dump the lumps into the continuous crusher. Secondary crushing stages follow, with dump trucks dumping the ore into the crusher for screening and continuous crushing to achieve finer particles. Finally, the screened material is separated to meet specific size and quality requirements. The mesh production process begins with line and cross wires unwound from coils placed on 3-ton payoffs. Wire detecting sensors ensure accurate monitoring before the wires pass through the first straightening unit. The feeding unit moves the straightened line wires into position, forming loops in the loop unit for tension control. Then the second straightening unit prepares the cross wires, which are accurately positioned by the servo-controlled pitch adjustment system. Cross wires are fed into place by the crosswire feeder and welded to the line wires at high speed up to 120 cycles per minute. The welded mesh then moves to the mesh cutting unit, where it is cut to the desired length. A roller ejector transfers the mesh to the automatic mesh winder unit, which rolls the flat mesh for easy handling and storage. This efficient sequence ensures high speed and precise mesh production. At the production site, workers use LAP laser projection systems to precisely mark positions for windows, sockets, and built-in components on empty casting tables. Guided by laser projections from CAD drawings, workers place steel plates and magnets to fix elements in position. Throughout production, they verify alignment using remote controls. Once all elements are correctly positioned, concrete is poured. After pouring, the laser system allows for inspection and fine adjustments. This process eliminates manual measurements, ensures high accuracy, and minimizes errors in positioning, enabling efficient and reliable production of precast concrete walls for housing. The installation begins with the engineer setting grid lines and leveling shims. A banksman hooks chains to the precast panel, which is then lowered using a nail bar. Shims are used to level the panel's side. The panel is adjusted to create a 10 mm vertical joint and shifted 400 mm using a crowbar. Push-pull props are fixed to the panel and drilled into the ground. The first prop is adjusted to align with the existing wall, followed by the second. Then both are locked in opposite directions to prevent movement. The banksman signals the crane to release the chains. Site tie steel is installed, and timber with wedges is used to shutter the wall bottoms. Corner brackets are bolted to the external corners. Finally, concrete is poured into the twin wall panels. During the first stage of the Liverpool Lime Street Station upgrade, engineers carried out key works to remodel platforms and improve infrastructure. This phase included the reopening of platforms 1 and 2 on June 11th. Concrete foundations were constructed for future platform extensions, and the platform surfaces were renewed. Track drainage systems were installed, while extensive track renewals and remodeling were completed to support longer trains. Engineers also upgraded and rewired overhead line equipment to power electric trains, preparing the station for increased capacity and more reliable service. Signaling systems were modernized to improve train frequency and operational efficiency. This initial stage, part of an 8-week transformation project, lays the groundwork for longer, more spacious platforms and enhanced train services. Platforms 1 and 2 will remain in operation until July 13th as further stages of the project continue. The terrace renovation begins with removing the old ceramic tiles and creating a cement screed with a minimum 1.5% slope toward the edge. Along the terrace edge, a 3 mm deep and 80 mm wide step is formed. Next, the W30 drip edge corner profiles from Renovation are installed by marking, drilling, and mechanically fixing them with polyurethane and expansion plugs. A string line is used to align the straight profiles, which are mounted in the same way, leaving 2 mm gaps between sections. Where profiles meet the wall, space is left for a bumper. A geotextile layer is spread across the terrace surface. A PVC-coated strip is attached to the wall, and a PVC membrane is heat welded to it for waterproofing. This membrane is glued to the edge profiles. The paving tiles 60 x 60 centimeters are then placed on adjustable smart pedestals, supported at corners and mid-edges. For added stability, a small amount of polyurethane is applied beneath each pedestal. Finally, a C10 base profile is mounted. The entire renovation is completed in 7 hours. The application begins by cleaning and preparing the wall surface to ensure it is solid, dust-free, and slightly damp. Component A, a fiber-reinforced bitumen emulsion with polystyrene granules, is mixed thoroughly with powder-based component B, the curing accelerator, to form a thick, non-dripping paste. Porous or absorbent surfaces are first primed using a diluted version of the same mix. The bitumen paste is then applied using a notched trowel, each approximately 1.5 to 3 millimeters thick. The first layer must dry before applying the second. Application should be done in dry conditions above 5 degrees Celsius. Freshly applied layers are protected from rain and direct sunlight. For further finishing, the still sticky surface can be sprinkled with sand. The final waterproof coating adheres well to vertical surfaces, and bridges cracks up to 2 millimeters. The ballast cleaning process using the Matisa C75 machine begins with positioning the machine on the railway track. The compact design and short ramp-in capability allow for quick setup, even on limited worksite lengths. Once deployed, the machine continuously lifts the track, enabling access to the ballast bed. The excavating chain removes the fouled ballast from beneath the sleepers and directs it into a screening unit. This high-capacity system can excavate up to 1,000 cubic meters per hour of ballast and clean up to 750 cubic meters per hour. Inside the screening unit, reusable ballast is separated from fine particles and debris. The cleaned ballast is then returned to the track bed, while the waste is conveyed into spoil wagons or discharged to the side, depending on site conditions. Throughout the process, the machine's guiding system ensures precise operation, maintaining alignment, and full use of the working gauge. The ergonomic cabin allows operators to monitor and control all functions via clear control panels and display systems. Cameras provide continuous visibility of the working tools, eliminating blind spots and enhancing safety. As the cleaned ballast is redistributed under the track, the machine gradually moves forward. Its articulated chassis and motorized axles provide flexibility and traction over varying terrain. Once cleaning is complete, the machine quickly ramps out, leaving a stable, clean ballast bed ready for tamping and track alignment. This continuous process increases efficiency, minimizes downtime, and ensures high-quality track conditions across heavy load, high speed, and conventional lines. The tamping process begins by correcting the track's longitudinal level and alignment. Then, tamping tines penetrate the ballast from above and compact it beneath the sleepers, using a squeezing motion. All tines operate with uniform, constant pressure and vibrate at exactly 35 Hz for optimal compaction. This method, known as non-synchronous constant pressure tamping, creates a stable sleeper bed and ensures precise track geometry. The process restores ideal track position and produces a well-compacted ballast layer, enabling smooth and safe railway operation. The repair begins by cleaning the wide crack thoroughly, using compressed air and heat to remove debris and moisture. Next, gap mastic is heated in a melter until it reaches the required viscosity. Once ready, the hot mastic is poured directly into the crack, filling the void completely. A squeegee is then used to spread and level the material evenly over the surface. While still hot, high-strength aggregate is broadcast onto the mastic to enhance durability and provide skid resistance. After cooling, the repaired area forms a flexible, adhesive, and load-bearing patch that integrates seamlessly with the surrounding pavement. This process ensures long-lasting, stable repairs that accommodate pavement movement and prevent future water infiltration or failure. The road marking process begins with the operator driving the SM400 along the road. The equipment sprays white paint through nozzles located on the left. The spray is manually controlled to ensure consistent spacing and thickness of the lines. As the vehicle moves, clean, precise lines are applied directly onto the asphalt. Workers behind the vehicle drop traffic cones to mark the painted lines. For detailed work such as pedestrian markings and lettering, a handheld spray gun is used. The operator occasionally stops to adjust the nozzle or refill the 400-liter paint tank before continuing the marking process. The process begins by positioning the preformed thermoplastic arrow precisely on a clean, dry asphalt surface. Using a propane gas torch with a wide flame nozzle, the operator heats the material at a consistent distance, moving the flame uniformly across the entire surface. The heating activates the embedded glass beads and melts the thermoplastic to form a strong mechanical and chemical bond with the pavement. Special attention is given to the arrow edges to prevent lifting. The material softens and conforms to the road texture. After sufficient heating, the arrow integrates fully with the substrate. Once cooled, it forms a reflective, skid-resistant marking that is durable under traffic and weather exposure. The chip seal process starts with a distributor truck spraying a thin, even layer of hot asphalt emulsion onto the existing pavement, ensuring consistent coverage across the surface. The emulsion, a blend of liquid asphalt, surfactant, and water, is applied carefully to create a strong bonding base. Immediately after, a chip spreader distributes finely graded aggregate uniformly over the hot emulsion, covering the entire treated area. These aggregates, often pre-coated with about 1% bitumen to enhance adhesion and reduce stone loss, are spread at a controlled rate to achieve optimal thickness. Next, heavy rubber-tired rollers compact the aggregate into the emulsion, embedding the stones securely into the binder. Multiple passes of the rollers ensure the aggregate is firmly seated, creating a stable, paved surface with a uniform texture. After the emulsion sets, workers sweep the road to remove excess loose stones, preventing hazards like chipped windshields or loss of vehicle control. Optionally, a fog seal is applied over the chip seal to further lock in the aggregate, enhance water resistance, and give the surface a smooth black appearance. The process concludes with a final inspection to confirm the surface is even, durable, and ready for traffic. The chip fill pothole repair process begins by cleaning the damaged area with a broom and high-pressure air blower to remove dust and debris. Once the pothole is clean and dry, chip fill thermoplastic granules are poured directly into the hole. A heat torch is then used to melt the material. As it is heated, chip fill softens and conforms to the shape of the pothole, ensuring full contact with the road surface and a tight bond. The technician spreads the melted material evenly to completely fill the hole and create a smooth surface. After a short cooling period, the repaired area will harden and be ready for traffic. For larger potholes, agrofill is first added to fill most of the depth, followed by a coating of chip fill. This two-part system ensures a strong, durable repair with minimal disruption to traffic. The process is fast, efficient, and can be performed in a variety of weather conditions. The switch renewal operation begins with the loading of the new switch and crossing units onto the Matisa WTM transport wagon at the factory. Each unit, composed of long bearers up to 4.8 meters, is fully pre-assembled and secured using a fast and adaptable clamping system. The WTM wagon, with a load capacity of approximately 40 tons and a total weight of 40 tons, is specially designed to carry oversized track panels while respecting strict clearance profiles. Once loaded, the wagon is integrated into a freight convoy and transported at speeds up to 120 kilometers per hour directly to the job site. Upon arrival at the first switch renewal location, track workers begin by disassembling the existing turnout. Using hydraulic hand tools and cutting equipment, they remove fastenings, clips, and connecting plates. The old rails and bearers are then detached section by section. A rail-mounted crane lifts the old switch components and loads them directly onto the now empty sections of the WTM wagon. The site is prepared for the new installation by clearing ballast and precisely aligning the foundation. The crane then unloads the new S&C panel from the WTM wagon. With assistance from ground crews, it is placed in the correct position. Long sleepers are carefully supported and adjusted using positioning devices. Workers secure the unit by fixing the rail clips and checking alignment, levels, and joint gaps. Willie Other. The second renewal follows the same procedure. The wagon moves to the next site, where crews repeat the removal of the worn switch and the installation of the pre-assembled replacement from the WTM. Each switch panel is treated independently, allowing high flexibility regardless of sleeper material, concrete, steel, or wood or switch configuration, with or without drive systems. The fast clamping system on the WTM greatly reduces handling time. Once both switches are installed, the WTM wagon, now fully loaded with the dismantled old switches, returns to the factory for disassembly, inspection, and recycling or reconditioning. This just-in-time method ensures minimal disruption to traffic, reduces on-site storage, and significantly increases productivity during track renewal operations.